So we're chewing through this practice packet on Lewis dot structures and VSEPR. Now we have one final category we are able to tackle, okay? We now can determine if the overall molecule that I've drawn a picture for is polar or nonpolar, and we are looking for two things. Two things will make this molecule automatically be polar. If the outer atoms are different, that will make it polar. In other words, there will be some sort of asymmetrical distribution of dipoles. If the molecule does not have if the molecule does have lone pairs on its central atom, that will create an asymmetrical distribution of dipoles. So different outer atoms or lone pairs on the central atom, those are the two things. In any one of those two things, just one of them is required, it'll make the molecule polar. So look in here. Let's look at my guy right here. I got water. We drew this Lewis dot structure. He has got lone pairs on the central atom, so he is going to be polar. And if we want, you don't have to do this to justify, but I think it is useful. We have lone pairs on Ca, or central atom. That's what makes that molecule polar. This one down, this is a funny one. There's only one bond because there's only two atoms in this molecule. So if there's only one bond, we're really looking at is that bond is polar or non-polar to determine whether the molecule is polar. Well, it's two coins. They are exactly the same thing. We know the difference in electronegativity between two of the same thing is nothing, right? So I've got a non-polar bond here, which means it's a non-polar molecule. So non-polar. And the reason for that is that we have identical atoms. It's just they're the same. So difference in electronegativity is 0. Next one down. I have same outer atoms and no lone pairs on the central atom. If all the outer atoms on the same and there's no lone pairs, both of those two things you need in order to be a non-polar molecule. So we have same outer atoms, and we have no lone pairs. Okay. Next up, I've got the same outer atoms, but lone pair on the central atom. We're polar. Next one, same outer atoms, but no lone pairs on the central atom. Non-polar. See how it's all about what's going on? The outer atoms and the lone pairs on the central atoms, right? So what this means, even though they're 3 resonance structure, I do not care. They all have the same outer atoms and there are no lone pairs on the central atom, which means those dipoles of each one of those sulfur to oxygen bonds are going to cancel each other out. Let's see if we have a few more we wanted to. Same outer atoms, no lone pairs on the central atom, non-polar. Same outer atoms, no lone pairs on the central atom, non-polar. Look how fun this is and satisfying. Uh-oh, we got two things. Meaning we have a bond. Whatever the bond is whatever the molecule is going to be. Is this bond polar or non-polar? They are different atoms, right? So I'm hoping that their electronegativity difference is so different that it'll put them into that polar covalent region. And I can totally check. Bromine's got a 3. Hydrogen's got a 2.2. The difference between 2.2 and 3 is 0.8. And that is an electronegativity difference that will be great enough to be a polar covalent bond, right? So we're going to call this a polar molecule because we have different atoms. So we could say, look at electronegativity difference. So electronegativity difference. Cool. All right, next up, same outer atoms, lone pair on the central atom. That lone pair makes it polar. Different outer atoms. I can stop right there. We got different outer atoms. That means there will be some sort of net molecular dipole. We do have a polar molecule. Okay. I think we'll do one more right here. I think that's the only one that we've done another example for. Yes. So we'll stop after this last one because I think that these molecular polarity things, once you figure out how to find a polar molecule, can kind of go pretty quickly. So this will hopefully be a real fast assignment for y'all to finish on your own without much help from me. But we're going to do one more example together. I don't care if it's resonance, just pick one resonance structure and look at it. Same outer atoms, but there's a lone pair on the central atom. That lone pair does a lot of work. It is making that molecule be polar. Okay, so that's the deal. You're going to be polar if you have different outer atoms or a lone pair on the central atom. If you do not have those things and you do not have both of those things, you will be nonpolar, because that will lead to a canceling out of the individual bond dipoles, which leads to symmetric, or the molecule itself being symmetrical.